planning kinematic trajectories. There were timing constraints on how long you were allowed to plan, like a minute of planning time. You could plan pretty sophisticated trajectories for walking over rough terrain where obstacles, you had to move your legs around obstacles. Are pretty significant kinematic constraints. We got a little bit more dynamic when they could put things like steps in front of us. We find a way to scoot up the steps. Still much slower and more embarrassing than your dog at home, but we were pretty happy. See, you've got to dive into gold, get that last second out of there. Okay. So that was encouraging that we could walk sort of kinematically over the rough terrain. Those gates were almost dynamic. But then now we want much more out of Little Dog Robo. We're trying to make him bound. This is Little Dog bounding on flat terrain. Bounding is incredibly hard because its motors are saturated almost completely. This is the most dynamic gait we could find Little Dog mechanically capable of doing. And now I'm going to tell you about trying to bound on rough terrain. Okay? So perching on a wire, bounding on rough terrain, these are two examples from our work of experiments that we want to be able to do to be able to synthesize very high performance controllers for. So the question is, how the heck do you do that, right? So it's hard for a few reasons. First of all, in both cases, the dynamics of the plant are very nonlinear, okay? We also had limited control authority. In the perching plane case, you could just count. I have one actuator and 7 degrees of freedom, roughly. If you think of the elevator as being inertialess. The motors in both cases are saturated most of the time. We've got a little dinky actuator on the glider. We've got relatively big actuators on Little Dog, but we're pushing them to their velocity limits. And basically, those two things add up to say, the nonlinear dynamics we had before, those matter. I can't just squish my dynamics with feedback, right? So the nonlinearities matter. And I don't think these are artificial examples, right? So you give me your favorite robot, and I'll try to move it fast enough that the dynamics matter, right? So I think as soon as our robots start really pushing the dynamic limits of what they can do, then I think these effects are going to be real. The other thing that Little Dog in particular demonstrated is some of these problems are not just dynamically hard, but they're sort of combinatorically hard, right? So planning over rough terrain, for instance, you have a combinatorial problem, almost like playing chess. Do I put my foot on this rock or just jump over that rock, go to the next rock? And there's something that feels naturally like a planning problem expressed in there too. So we want to somehow marry the two types of techniques. So how do we design high-performance nonlinear controllers with limited control authority? I want to tell you a way that we are combining the combinatorial planning type algorithms with convex optimization-based nonlinear